think last time we were doing observability exploration kind of stuff, right? So let me write down the definition again, because last time we had a question on the definition which wasn't very clear. Just to recap, we were at observability. The RTI system is observable if at initial state can be this slide. I'm sorry. I'm so sorry. We had that, so that's not the problem. The problem was, what is an unobservable state? Okay, we made the definition last time, so that's not the problem. A state, that was a statement. X star is not equal to 0, is unobservable. So you don't have to write this. I mean, I have written this last time. If the 0 input solution y of t with x star all t greater than 0. Okay, so this was the definition for the unobservable state. A state is unobservable, right? So here's what it says. Here's what it says. It says if you're here, okay, and this is your initial condition, let's start here, which is not the 0 point. The 0 point here represents the equilibrium point, okay? This is here the equilibrium point. This would be here the equilibrium point. This one, let's make it red. This is the equilibrium point. So, if a system is here at the equilibrium point, then it would stay there forever, right? Now, if the initial condition is not the equilibrium point, let's say it's over here, and you don't touch it, which means 0 input solution, there's no input, what would you expect this point to happen? You would expect this point to move somewhere, right? Because it's not the equilibrium. If you start here, and you don't have an input, right? And it is not the equilibrium point, it should move somewhere. I mean, x1, x2, let's have a two-dimensional system like this. I mean, it's just like saying this. Let's say you have a pendulum and you start here. And you just leave it. Don't touch anything. What's going to happen? Is it stay here? Is it going to stay here? No, right? It's going to start moving. So we know it's going to move. The only place it would not move is the equilibrium point. If you start here, it will not move. That's the definition of the equilibrium point. So it would not move over here if this is the equilibrium point. However, if you start here, okay, which is not the equilibrium point, then we know it's going to move. Okay? So, because it's going to move, you should see something in the output. Right? So what it says is that if you don't see anything in the output, okay, then that state is unobservable, which means we know it's moving, but we don't see anything. You see? That's what the definition is. A state x star not equal to 0, not equal. If the 0 input solution, okay, no input, u is equal to 0, u is equal to 0, no input, y of t with x0 is equal to condition is 0 for all y. So y is equal to 0 at all times, although we know as time goes by x star, I mean x is going to move somewhere. Right? It's going to move, I don't know where, but it's going to move somewhere because it's not the equilibrium. So if I measure still 0, then I know this state is unobservable. I can see it. Does that make sense? Okay, so that was the definition. So this is where this whole thing is building, okay? The whole unobservable idea. And then we said last time, again, theorem, we said an LTI system is observable if and only if it has no unobservable states, right? That was kind of the theorem. An LTI system is observable if and only if it has no unobservable state. Okay, so we don't want this to happen to any of the states. We don't want this to happen to any of the states. Okay, so if that is true, then we know the system is observable. And I think I wrote this down last time, so you don't have to write it again, but let me just write it down so we can move. So basically what we are saying is, if you have a system like this, x dot equals ax, and no input solution, which means u is equal to 0, right? That's what it means. No input. The output, c of x, where we also say d is equal to 0, to make things easier, we say, if that's true, then we should not see 0. I mean, the output should not be 0 if you are not at the equilibrium point. If the starting point, right, is not the equilibrium point, right? For a linear system, the equilibrium point is 0, right? If you don't start at the equilibrium point, all right, then, and you don't have an input, then the output should not be equal to 0 at all times, okay? And if I'm writing this as if they were scalars, but you know, if this is a vector, then you might want to write vectors here, okay? So this is kind of the condition. We don't want zeros as outputs if I don't start at the equilibrium point, okay? And if I don't give an input. Because if you think of this example, if there was an input, for instance, if I would be holding this, which would be an input, then it would not be moving, right? I mean, I could make it such that, I could make the input such that it is not moving, or I could move it left, right, whatever, right? So input, no input, and all that. So this is the condition we are looking at. And this is precisely how we are going to do the test of our observability. So let's say I want to have a solution of this. The solution of this would be like this, e to the power at x of 0. Right? This is the solution of this thing. So if x0, the starting point, is not equal to 0, I don't want the output, y of t, to be equal to 0, right? That is the condition. So it's this thing. So you get a solution for this a to the power at, which we have done last time. So the output would be y of t is equal to c times k is equal to 0, n minus 1, alpha k of t, ak x of 0. Okay? That is the solution. All right, so let's write the solution a bit nicer. 0, n minus 1, alpha k of t, c, a, k, x of 0. And this alpha here is just some coefficients that will appear if you that you can calculate based on this matrix A. So this would be represented like that. And this is something we got hopefully from our calculus classes. All right, so if you open this up, here is what you get. Y of t is equal to alpha 0 t c x 0 plus alpha 1 t c a x 0 plus alpha 2 t c a square x of 0 plus plus alpha n minus 1 of t c a to the power n minus 1 x 0. Okay? So this is your solution, all right? No input. X0 is the initial condition, and y is the output, okay? So what was our condition? What did we want? We said if x0 is not equal to 0, right, then we don't want y to be equal to 0. Okay? Now, if x is equal to 0, x0 is equal to 0, of course the solution will be 0, and which is the trivial solution for this, and which is kind of expected, because if x0 is the equilibrium point, then the output y must be equal to 0. It's not moving anywhere. I mean, right? That's what we are expecting anyway. However, now we are saying x0 is not equal to 0, and y, the output of y, should not be equal to 0. Let's first look at the condition. What is the condition over here for y to be equal to 0 when x0 is not equal to 0? What would be the condition? What should these things satisfy? Imagine that alphas are just coefficients, right? They're just coefficients. So forget about that. They are just coefficients. And then you have these matrices. You have the C, CA, and so on and so forth. Remember when we looked at the beginning of the semester, we looked at linear independence, or we looked at linear dependence. We said, if you set this equal to 0, right? If you set this equal to 0, then if x0s are not equal to 0, right? And you can write these, then we say these things are linearly dependent. Remember that? Basically, if x0s are not equal to 0, and you can write this equation to be equal to 0, then we say there's linear dependence between them. Because you can write, for instance, one of the coefficients, you can write this as a function of the other stuff. Remember that? A little bit? Yeah? Remember that a little bit? If you can write this, then you can write this as a linear function of the other element, of the other terms in this equation, if this is equal to 0. Okay? So, which means then there is linear dependence between these pieces over here, if this is equal to 0. So, if this is supposed to be not equal to 0, then what we need to say is that there is no linear dependence between these pieces over here. Look at that piece of paper on the sheet that we looked at on the linear independence arguments. Okay, there was a definition for linear dependence. It basically said, if you set this equal to 0, if you can set this equal to 0, and x0 is not equal to 0, then these pieces here are linearly dependent. Okay? So because you don't want to have it equal to 0, that means you want linear independence between these things. And linear independence, of course, also means you want to have full rank in these matrices. So let's see if there's anything. Okay. So, which means these pieces here, you want linear independence. So C, the matrix C, CA, CA square, are linearly independent. Right, that's what you need. You need linear independence for y not equal to 0. Which also means then, of course, that C, CA, CA square, CA n minus 1 is full rank. If that's true, then LTI is observable. Because that means no matter what x0 is, unless x0 is equal to 0, we will never get this. Right? That's what it means. We will never get this. We will never get the output to be 0. There will be always another solution. So in order to have that, we need to have the linear independence over here. Okay. One way of looking at this is, of course, you can look at it from a discrete time point of view. I mean, if this is one argument. Another argument is the discrete time solution of xk plus 1 is equal to a times xk. Right? You can look at this from, I mean, we always look at continuous time, but you could also look at discrete time, k being one step, right? And then the next step would be a times ak, that would be the next step, and then so forth, so it moves on, right? And yk is equal to c times xk. I mean, in this class, we really never work in discrete time, but I just think that this explanation for observability, for the observability test in discrete time is kind of neat. So that's why I wanted to include it here. So the discrete time solution would look like this of our continuous time solution. So then at time 0, the output would be c times x0, right? I mean, at the beginning, the initial condition. And x0 being not 0, of course. So the next time step, when this is for k is equal to 0, right? This is for k equal to 1. This is the discrete time. This is how you do it in a computer, right? When you propagate in time, you go one time step, another time step, another time step. This is exactly what you do, actually, in a computer. You can't really do the continuous time. So y1 would be equal to c times x1, right? Because you would get x1 is equal to a times x0, right? And so on and so forth. So this would just continue, and therefore this would be ca x0, right? So you continue for the second time step, you would get c times x2. That would be c times a square times x0. And this would go to y of n minus 1 all the way to c a n minus 1 x0. Okay? So you look at these numbers here. Can I write this down now? Look at the discrete time solution. It looks like this. y0, y1, y2, yn minus 1 is equal to ca square, ca n minus 1 x0, right? That's a discrete time solution. So, if you want to have, I mean, if x0 is equal to 0, if this is equal to 0, then this becomes equal to 0. That we know, right? But if x0 is not equal to 0, and you want a solution over here, just like in this case, if you don't want this to be equal to 0, then you better have linear independence over here. Okay? So you have a solution on this side. In fact, a unique solution. Linear independence. Or you really want full rank. Okay? And this is, and this here is what we call the test for observability. Okay, so let me give you an example, and then maybe we can talk about this a little more. Remember, we had an example that looked like this. X dot is equal to -2, 0, 0, -1, x1, x2, plus 2, 1, u, v0, x1, x2. Remember, we had this example, and we kind of figured it out. We kind of said that there's something wrong because one of the states we can't really observe. And remember, the one that we couldn't observe was x2 because we are measuring x1, that's fine, but x1 and x2 are literally independent from each other in terms of how the dynamics, how they influence each other, right? So x2 was not influencing x1 and vice versa, and I could only measure x1, so we said we cannot really see x2. So, I mean, according to what we have described, it should be unobservable, right? All right, so let's look at it. The question is it observable? First of all, the size is 2, so n is equal to 2. So according to this, according to the test over there, the test would look like this: C, CA, right? And we want this to be full rank. So you put it down, you put 3, 0. Here we're looking at A and C. That would be -6 and 0, right? And you look at the determinant of this. The determinant of this matrix, let's call this the observability matrix. Determinant of O will be equal to what? 0. So it is not full rank, right? And therefore it is not observable. This system is not observable. Because, now coming back to this definition, there will be states, I mean there will be paths on the states, on the system, where when you start at that point, the output will appear to be 0. The reason is, although x2 is moving, if x1 is not moving, you would measure a 0. You would measure a 0 output. There would be states where you just measure 0, although the system is moving. Let's say x2 is changing, and x1 is not changing in this system, right? So if x1 is not changing, you get 0 over here. If x2 is changing, x2 is not influencing x1, so x1 will not change either. So basically, you will just see 0 as an output from that starting point, I mean, okay? So maybe one more example. I mean, this was kind of an obvious example because we did this at the, last week where you had these zeros and you said, oh yes, it is unobservable, we could see it. But let me give you another example where it is maybe not very, where it is not as obvious as this one. 1, -2, -3, -4, x. So what do you think? Do you think this system would be observable or unobservable? It's difficult to see, right? I mean, it looks observable. I mean, here we could see the zeros and everything. It was kind of obvious. But here it's not obvious, right? So you want to make a quick test? Just try it. Tell me if it's observable or unobservable. You have to calculate A times C, right? You need to calculate this, 1, 2, 1 minus 2 minus 3 minus 4. Is it 0? What do you get? Minus 6? No, minus 5, right? Sorry. Minus 5, minus 10. Minus 5, minus 10. And look at the determinant of this. And you'll get 0. So it is unobservable. Unobservable. What does it mean? It means that this system has states that are unobservable. It doesn't mean that everything is unobservable. We can't see any of the states. That's not what it means. Obviously, we will see something when you start starting the system. But there will be states. There will be states that will be unobservable. Therefore, we call the system unobservable state, unobservable LTI. Or we would rather say the LTI is not observable. It's not an observable system. Okay, so let me look at another example. Any questions, first of all? Does it make sense? All right. The observability is sometimes a little bit more. I always found it a little bit more difficult to explain than controllability. Example. Let me make it a bigger system. So 1, 2, minus 2, 3, minus 4, 5. Okay. And, oh yeah. First question, is it observable? No, controllable, sorry. Because it's a 3 by 3. It might be, might look a little more difficult, but I will show you a few tricks. Now, let's not check. Is it controllable? Let's make it formal. Is the pair AB controllable? Is the pair AB controllable? This being A, right? This is the A matrix, and this is the B matrix. So, question is it controllable? So, according to our controllability problem or test, we need to calculate BAB, A square B. Now, the first one is easy, right? Well, you just write B. 0, minus 1, 2, minus 3, 4, minus 5. So, let's write AB. Okay, write the first line. Let me just write it. It's minus 6, 7, 12, minus 10, 46, minus 55. And then you have this one, which is a lot more. You need to have A squared and then multiply it with B. But what should be the rank so that we can call this a full rank? I mean, obviously this will not be a square matrix, therefore we cannot calculate determinants like we did over here. But we need full rank for this matrix. When would I call this full rank? Is it enough if I have rank equals 3 because I have 3 rows? Or should I look at all the columns? Well, the rows cannot have more than 3, right? I mean, it has to be 3. Okay? So if the rows are linearly independent, I would still call it a full rank matrix. So all I really need is rank equals 3 to call this a full rank. Okay? So this part I didn't calculate, these ones, but all I am going to really look at is look at these 3. If they are linearly independent, the rank is minimum is 3, right? So you don't have to really calculate the rest of it. Are they linearly independent? It's hard to say. You can look at the determinant maybe, but you can just see by looking at the numbers, there's probably nothing that you can multiply or add to each other to obtain this one. So I can just look at this. I have a 0 here, minus 6. I have a 46 over here, minus 5 or 4. I can probably safely say that this is minimum rank 3. Okay? So I would call this a rank 3. And therefore, I would call this full rank. And therefore, I will call it controllable. You see how I did it? I didn't calculate everything. Even if I calculated everything, I wouldn't know how to check full rank. But I can safely say if 3 of these columns are linearly independent, at least I know, even if they are linearly independent, at least I know the column rank is 3. And the row rank, all I need is rank equals 3 because the row rank cannot be more than 3. Okay? So this would qualify already as a controllable matrix without looking at the rest. What else? Let me give you one more example.
So we know the maximum is 3 for the columns, but how are we sure that the rows are linearly independent?
These rows? Well, they gotta be if I have 3 linearly independent columns. Okay? There was this one you might want to read about this a little bit more, about these column ranks and row ranks. I know I went a little fast on this, but if we know there's linear independence in here, then we are sure that there is linear independence over here. Okay. I think there was a question when I was explaining the ranks, and someone told me that we had a discussion, I don't know with who, about row ranks and column ranks. So this is something probably you might want to just freshen up, okay? But basically the answer to your question is yes. Okay. Another one. Can you do this real quick? Let's look at the controllability real quick. Now this is a third order system. So it would be very similar to this. It would be B, AB, A square B. This one? No, it's a controllability. And here we would be looking at C, CA, and CA squared. So let's give a break. I mean, I'm going to give a break, but you can try to find this and then give the break. Or you can wait for the next hour for me to give you the solution.